Bonjour à tous. Nous recommençons aujourd'hui notre cycle de conférences du campus et nous accueillons aujourd'hui deux invités étrangers, Hannes et Russel. Et donc, c'est une première, on va faire cette conférence en anglais. Pour eux, ça va être facile, pour nous, peut-être un peu moins, mais je compte sur vous, en particulier pour les questions, pour être à la hauteur. So, welcome, Russel and Hans. We are very pleased to welcome you, and it's the first time we are doing this conference in English, so for you it will be easy, but for us, maybe a little bit less easy. The conference is about innovation, about robots and construction. So innovation and construction, of course, are main topics for SETEC. We are at the heart of the SETEC concerns. And when thinking about this conference, I remember an article I read not a long time ago, speaking about venture capitalists working in the Silicon Valley with high-tech industries. Mr. Mark Andreessen, I think he's very successful, so very well known in this area. And he said, of course, he wants disruptive innovation society. Sorry, he thinks that people doesn't have to be afraid about being replaced by robots, but they have, on the contrary, to look for more innovation and for a change, a faster change. This was a debate during the last campaign in France about robots taking the jobs of the people. But here, what interested me is that he makes a very interesting analysis of the economy. He says that in the economy we have fast sectors. Fast sectors are those eaten by software. And when he thinks about fast sectors, he thinks about retail, about media, and probably today about transportation with ride sharing and also with self-driving cars. So those sectors are sectors in which the prices are going very, very low and the economy is changing. But there are some slow changing sectors, and those for which the prices are still high and there's no really, how to say, competitiveness advantages. And he thinks about construction as a slow-moving sector. And he addresses a challenge to the Silicon Valley people, that's to say, you have to now take care about that sector and to put the high-tech industry in order to change and to make this sector a very fast-changing sector. So the challenge is set for the Silicon Valley industries, but of course we have also high-tech industries in Europe, and we are very glad that you will talk today about the improvements and the changes that you are bringing into that industry here in Europe. I think that Audrey is going to present you in more details, introduce you in more details.
Hello, I'll be very short and just add a few words. In the context of SETEC Innovation Labs, we spent some time reflecting on the robotics and digital manufacturing techniques in architecture and construction. How do these techniques change the construction processes? How do they change also the way of doing structural engineering? And all the way up, how do they change the way of thinking and drawing architecture? So that was those topics. And to find some answers, we went to a fabulous conference in Stuttgart last April called Fabricate, where we saw that actually there are hundreds of designers, architects, engineers that use these techniques for real in their daily practice. And we met people from Gramazio Kohler research office from Zurich, and we were very impressed to see their work. They are pioneers in these topics. They've been researching on these topics for 10, 12 years now, and we are very happy that they accepted to come and share their knowledge with us. So we have two representatives, let's say. We have Hannes Meyer, who is the Director of Education at Gramazio Kohler Research. So he gets to see all the research works passing through his desk. And Mr. Loveridge, who is now Managing Director of the Swiss National Center of Research in Digital Fabrication. But he will start speaking and explain more in details what it is. And we will have two presentations of more or less half an hour each, and then you can ask your questions afterwards. You can also ask your questions in French if you're shy, because Russell speaks French too.
Merci Audrey. Alors, merci pour l'introduction et aussi merci pour l'invitation. Oui, mon nom est Russel Loveridge, je suis le directeur général de la Pôle nationale de recherche en fabrication numérique. Nous sommes un groupe d'à peu près 100 personnes et comme nous sommes très internationaux, on a des chercheurs de, je pense, 23 différents pays. Comme nous sommes très internationaux, la langue commune, c'est anglais. Alors, je m'excuse, mais je vais changer en anglais maintenant. Yes, so that's me. So I'm the managing director of one of these things called an NCCR, a National Center of Competence in Research, un Pôle National de Recherche from Switzerland. And these national centers of competence are the highest funded research bodies in Switzerland. And typically, these research bodies focus on kind of objective science, so really science. So we have NCCRs in particle physics, and we have NCCRs in RNA and DNA, and we have NCCRs in ultrafast lasers. And so we are extremely proud to be the first NCCR which is really working on applied sciences in the area of architecture and construction. And the NCCR Digital Fabrication, then we started in 2014. We're a consortium of a group of different universities across Switzerland. So Gramazio Kohler from ETH Zurich is one of the chairs from one of the universities which is in our group. But we also have representatives from the EPF in Lausanne, from the Berner Fachhochschule, the University of Applied Sciences in Bern, and also from the Swiss National Laboratory for Material Sciences, as well as, of course, our home institution, the ETH. We're approximately 100 people in this research consortium. And then in addition to that, we also have a Master's of Advanced Studies program. So altogether, we're in the range of 120 people from various backgrounds who are bringing their attention really into this area of innovation. Now, NCCRs are an extremely important research method or a research center in Switzerland because they have a 12-year mandate. And so if any of you have done a doctorate, you know that a doctorate lasts for about 4 years. And most research funding that happens at the very high level around the world is usually approximately 4 years worth of research funding. So the opportunity to have 3 generations of PhDs or 3 generations of research cycles on a single topic, and then to have that over a wide range of disciplines means that we can make a very significant impact over time in this area. And this is really the strong capability of these NCCRs. And of course, this is a strong capability of ours in the area of architecture and construction. So because these NCCRs are focused on topics of Swiss national interest, and engineering and construction and architecture is one of these areas of Swiss national interest, we have to ask ourselves, why would the Swiss government, why would the Swiss National Science Foundation fund such a project at a high amount of money for such a long period of time? And the very easy answer is this graph, which shows productivity in the manufacturing sectors over a 20-year period. And you can see that the general manufacturing sector, over a 20-year period, their productivity has gone up by approximately 50%. And you can see that the construction industry kind of hovers at the 100% level. So it more or less stays the same. Now, with this graph, I point out a couple of things. First of all, I point out that manufacturing grows time over time anyway, but that we took this graph to slightly represent the bringing in of new digital technologies and new fabrication techniques based on digital technologies in manufacturing. At the same time, we strongly recognize that the forces acting in the construction sector include things like the downplay in the economy, and also changes to building codes, changes to energy codes, and so on and so forth. So this is not to say that innovation has stayed stagnant in the construction sector. We're constantly needing to evolve what we do, but we tend to do it in reaction to things that are happening rather than being proactive for new technologies. And so when we go to the Swiss National Science Foundation and ask for umpteen millions of Swiss francs, we know that we're going to be judged by scientists. So we are architects, we are engineers, but we know we're going to be judged by scientists. So we need to place this innovation in a science capacity. And with architects and engineers in a société like this, you already know that there's a very different culture between your architects and your engineers. Architects are trained in a very subjective research methodology. Engineers are trained in a very objective research methodology. So to convince a bunch of scientists to give us a lot of money, what we had to do is place these research questions really in the objective sciences. So we chose the sciences of computation, of material systems, and robotics to found the types of technological research that we're going to do. But then these NCCRs are also required to create radical innovation in their area. So not just iterative innovation. This is what engineers and scientists are especially good at. You're especially trained to do is iterative innovation, whereas architects are trained to effectively do radical innovation. That's what design is all about. So looking at a problem, conceiving of a new way of looking at it, reformulating it, repackaging it, and coming up with a new response to that problem. So if you put 3 engineers in a room and you give them one problem, if they don't come up with the same answer, then you have a problem. If you put 3 architects in a room and you give them one problem, if they do come up with the same answer, then you have a problem. So this is what we reflected on, and we know that we have to come up with new and radical ways of approaching the construction industry. These technologies are coming. It's absolutely sure that they're going to come to the construction industry, maybe over time, as we heard in the introduction, but still we know they're coming. So how do we take these technologies and really create radical new ways of looking at construction and architecture using them? And this is why we really bring architecture over the center of the Venn diagram, and then the NCCR digital fabrication really operates in that collaborative center where all of these different disciplines come together and where new ideas can come out of that. So we created a team, of professors from all across Switzerland in various disciplines. And this is what's very important to understand, is that we as architects and as construction engineers, we immediately recognize that there is no way that we have all of the knowledge that is required to bring these types of innovations to light. So we knew that we needed to bring in roboticists, really specialists in mechanical engineering, but also specialists in control systems. We knew that we needed computer scientists. We knew that we needed material scientists. We knew that we needed a breadth of knowledge that would give us a basis for us to really implement some innovative work. But these are the professors involved, but these are actually not the important people within the NCCR. These are the people who guide things. But the important people within the NCCR is the fact that we have 100 people, all with different backgrounds, all operating at the PhD and postdoc level. So they all have experience. They all have experience in research. Most of them have experience in industry as well. And they all come with a specific knowledge of how they work within their area. And the challenge for us has not been bringing projects together. The challenge for us has been bringing people together. How do you get a roboticist to talk to an architect so that they understand what is important for the other one and that they can work together towards a common goal? How do you get a material scientist and a control systems engineer to understand what the common goal is? And so this is really the challenge that has been put forth for us in an NCCR. And this is also, of course, the challenge that you guys face in industry all the time, working with various trades, working with specialists from different areas. But really, to do this and also convince them to take leaps of faith, to do radical steps in innovation, this is the challenge that we're facing. But we actually know that we're on to something, because if you look at the technology issues from The Economist, in 2012, they were talking about the factory of the future. They were talking about 3D printing and the ability to manufacture things in very fixed and safe environments, and how this was going to change manufacturing. And then just 2 years later, they talk about robotics, how these technologies are coming out of the safe environment and are becoming contextually aware, they're becoming safe to work with people, and so on and so forth. So even in the 2 years where we were writing the proposal for this large national consortium, even in those 2 years, the technology was changing fast enough that we knew that we had to kind of reflect on this. Now, what is very interesting about these two covers is that it also directly relates to the ways that we construct things. We have two basic methodologies of construction. You have prefabrication and you have on-site construction. And both of them are useful for different things. Both of them are useful for creating very complex structures, creating very robust structures, creating architecture, creating infrastructure, but they have very different challenges associated with them. In prefabrication, of course, you have the nice closed environment where everything is protected. You can achieve efficiencies similar to a factory. On site, you have a bunch of different challenges related to how you can create things effectively. So we have then translated those into our two grand challenges of on-site digital fabrication. This is really taking the technology out of the safe environment and putting it on site. And at the same time, we also have bespoke digital prefabrication, which is using robots and using technologies in the kind of protected environments. And we have visions associated with this. So on-site digital fabrication, we already understand that robots will not replace construction workers. Robots will work in tandem with construction workers, because there's a whole pile of knowledge that is held tacitly by construction workers, which is incredibly difficult to program into machines. And what is perhaps the use of machines, perhaps the use of robots on the construction site, is that they're very good at doing the very simple, the very easy to program types of back-breaking labor that we would rather humans not do. And this will be the first implementation of robots on the construction site. And so we see robots changing from being these big, heavy machines to being much more lightweight machines, being much more fluid machines that can operate in conjunction with people and that don't pose as much of a danger to people as the robots that we know from current manufacturing facilities. At the same time, for prefabrication, we also know that the factory will change. So this is an image of our new facility in Zurich. This is the first kind of very, very large-scale robotic construction facility aimed explicitly at architecture. We can build a 2-story building in this facility using real materials at real full scale. You can see 4 industrial robots hanging from the roof, which gives us the full flexibility of the factory floor. And this is basically where we do a lot of our research. And you'll see a couple of examples of that, both from myself and Hannes in the next minutes. So getting back to the NCCR digital fabrication, we have these 2 areas of focus. We have kind of on-site construction, where we're looking at robots, taking them out of their space, giving them sensors, making them contextually aware, making them kind of able to work with humans on the construction site. And at the same time, we have prefabrication, which is really the question of how you build things, which you then transport to site. So a first example of this is active control of cable net formworks. So this is an active cable net. This is a net that is hung between spaces, which is then actually will be covered by a textile, and then we'll cast concrete directly onto this net. We have the ability to control the tension at the individual nodes within the net so that we can reformulate the shape of the net actively. So as you apply concrete to it, the net sags, we can tighten up the net and it will go back to its shape. And in that way, we can completely eliminate formwork while at the same time creating complex structures. Now, please pay attention to this slide. I'll show you something about that in a couple of minutes. We're also looking very clearly at building compression-only structures. If you can eliminate tensile members from within a structure, then you can eliminate a huge amount of the embodied energy within a structure. So if you can use computation to help you design very optimized compression-only structures, then you can rationalize the construction process and use different materials or use very simple materials to create very complex forms. We look at full architectural scale 3D printing. We have one entire chair, one working group that's looking at 3D printing as a way of moving forward in the construction industry. We look at kind of nominalized 3D digital fabrication, so milling and cutting, laser cutting, water jet cutting, which is used to look at existing low quality materials and find out ways of assembling them using different techniques to create very complex structures. So low embodied material, low embodied energy into highly complex structures. We look at the robotic joining of structures. So the easiest way to kind of imagine that is that a brick is the size that it is because a mason can lift and place a brick all day long. If you replace the mason's arm with a robot arm, then what's the size of the new brick? Because the robot arm you can make any size, and you can use it to twist and join things in very prescribed, very accurate ways. So all of a sudden you have new ways that you can join things together with only the force of a robot behind it rather than the limitations of the human hand. And then we can take that even further and say what happens when you have two robots working together. And so when you have two robots working together, you can actually use one of the robots to hold things in place while the second robot then positions the next piece. And you can completely eliminate structures, you can eliminate the scaffolding, you can eliminate formwork, you can eliminate all of the other componentry that are typically used to place things very precisely in three-dimensional space such that you're able to build up composite structures. Now, as you're watching the video, please pay attention to the sun because you'll get an idea of actually how slow this process is. You know, the structure was built over the course of 2 days because all of these things that we do are prototypical. We've never done them before. If we do them once, then we typically don't repeat it again. And that means that the processes that we're involved in, they tend to occur over longer periods of time. But we know that after we've done it once, we know how to refine it, we know how to take steps forward, and eventually the goal is to hand it off to industry. Switching out of the fabrication facilities and into kind of the real world now, we also do things like build mobile robots. Mobile robots that are equipped with sensors, mobile robots that are equipped with manipulators to be able to do things like build these brick walls, which the ETH is very, very well known for. But for example, this is a robot that can move itself around the construction site. It can move itself from one place to another, thereby effectively becoming a 3D printer, but rather than dropping little blobs of material to create something, it picks up building components, whether they're bricks or whether they're pieces of timber or whatnot, and that allows it to build structures that are much bigger than itself. It also has the ability to know its accurate position in three-dimensional space. So like a construction worker, if I move from one place to the next, I have a bunch of references that I can triangulate and then I can place the next piece. This is very, very easy for a person to do. It's extremely difficult for a robot to do. So a lot of the research actually on this platform was put into making sure that the robot knows accurately how, when it moves from one place to another place, it can continue to build with construction tolerances in sequence. Taking that up a level, we also do things like roboticize construction equipment. So I don't know if any of you have seen one of these before. This is a machine called a Menzimuck. This is a very Swiss machine. This is a machine that is designed explicitly to be able to work in mountainous terrain where it needs to be able to position itself on the sides of slopes or needs to be able to drive through riverbeds or whatnot. But each one of these wheels is an electric motor and they're on these individually actuated legs. And that means that the driver of this machine has 36 different controls to be able to just drive across the terrain. Now, what that means is that as he drives over irregular terrain, the machine is kind of jumping and bumping from one step to another because his ability to respond is based on the balance from his inner ear. It's based on his sense of balance, whether the machine is tipping. If you automate all of this, if you put sensors behind it, you can increase the frequency up to 100 times per second, and the machine can drive extremely smoothly with the wheels going up and down, and it can scoop up a big load of earth, and it can swing around as it's driving across irregular terrain, and the center of gravity of the machine remains stable and low enough to the ground to be able to accommodate this. So we're very interested in how we can use sensors and technologies to robotize existing pieces of equipment, and in that way give us new capabilities at much bigger sizes. So now you've seen a little bit of what we do. It's an extremely brief snapshot. What I want to talk to you about is now how we convince people that we're ready to actually take these technologies out into the real world. And what we, the NCCR, do is we create these things called demonstrators. And demonstrators are large, full-scale, often inhabitable buildings that we contribute to that allow people, especially from industry, to see that we know what we're doing and that they can take trust in what we're doing, and that the processes that we have developed are actually ready. They're insurable, they're reliable, and so on and so forth. And the first demonstrator that I want to show you is actually our home building at the ETH in Zurich. So this is a building called the ArcTech Lab. It was completed 1 year ago. We moved in 1 year ago. And this building is actually a test bed for a lot of the different technologies that were developed in the ITA, the Institute for Technology and Architecture. Hannes will show you the roof in a couple of minutes. You can just kind of see the roof in the black on the top. It's kind of a wavy, bumpy roof, and he'll explain to you how that came to be. But there's a prototypical HVAC system, heating, ventilation, air conditioning system. There are prototypes with regards to other building systems within it. The building itself is extremely, extremely lightweight. It's built on top of a pre-existing parking garage from the 1960s with only 12 points of contact that have punctured the parking garage. So the parking garage is completely intact. The building sits directly on top of it. And this bottom portion here, the bottom stem of kind of the mushroom, is this robotic fabrication lab, which you saw before. Another demonstrator that I want to show you, which hit the news for a while, and that is very, very Swiss, is the Monte Rosa hut. So the Monte Rosa hut started as an architectural design studio in one of the design courses at the ETH. And it went from that to some preliminary research investigations, and from there to real research projects, and from there to a construction project, and from there to the actual realization of the Monte Rosa hut. Now, the important thing to remember is that this hut is built up at 3,000 meters, and there's no road up there. So the driving parameter for everything, absolutely everything that went into this building, was weight, because everything was flown up by a helicopter. And at the price of several thousand francs per hour of flying time, the helicopter was also the crane which held the pieces in place as the building was assembled. So weight was the determinant in how the building was built all the way back, and most of the building was designed parametrically to maximize the weight and to maximize getting all of the components up to allow this building to be self-sufficient, both energy-wise and protection-wise, on the top of a Swiss mountain. And then the last demonstrator project that I'll talk to you about is called The Nest. This is a building that's been built on our campus at the Swiss National Laboratory for Material Sciences. The concept behind this building is that it's a series of platforms that allow different research groups from around Switzerland and around the world to build modules that will allow them to test ideas in building science and construction, and then place them on this building. The building provides all of the backbone services, the heating, ventilation, air conditioning, water, and so on, but it also provides monitoring systems. And this allows us to do research into kind of building science in a kind of semi-controlled environment, but then the modules are actually inhabited. And the NCCR Digital Fabrication is designing one module called the DFAB House. Hannes will talk a little bit about some of the technologies that are going into it. And we're also involved in a second project called the HILO. And the HILO is a project by the Block Research Group. And the driving design idea in it is this ultra thin concrete shell roof. And this concrete shell roof, I want to bring you back to this picture of the cable net. So you can see in the picture of the roof, you can even see the pillowing in the bottom of the concrete shell. This roof is being cast without formwork. So there's no scaffolding and structure that's going to determine the form of this. It's all a tensile cable net, which is strung between the buildings or between the sections that are already there. And then this is being controlled by placing a textile membrane on top of this net and then casting concrete directly onto that with a bit of carbon fiber reinforcement. So this is a short video of the process. The cable net was designed so that it could be dismountable and used again in other configurations. This is inside our testing hall, where this is a one-to-one prototype of it because it's never been done before, and because the concrete shell at its thickest is 12 centimeters, but at its thinnest is approximately 2 centimeters. So this is an extremely, extremely thin shell reinforced with carbon fiber, which you can see here. And then it's actually shotcreted, and they developed a vibrating hand trowel. So by hand, they pour the concrete onto it and then trowel it into place to get the desired thickness. And so you can see the teams building it up. Again, this is a one-to-one prototype, so we're building the roof twice, so that we build it first in the protection of the hall so that we know what we're doing, and before we actually take it up to the top of this building in the wind and in the rain and under all of the forces. So there you can see the end product. There's another picture of it here. So this is the component of the roof. It's quite like a cathedral underneath it, and it was up for a couple of weeks. But of course, we also need to pay attention to how these things come down. So what was very interesting to me is, of course, we had to dismantle it. We only have a certain amount of space in this robotic hall, and there are other experiments. But what's extremely interesting here is, just let me go back. What's extremely interesting here is, look at how little material is on the ground. So this entire shell, which could cover basically this room, had 4 cubic meters of concrete in it. And so not only does that mean low cost, I mean low cost in terms of the material, but it also means low embodied energy at the cost of a huge amount of information that was required to build it. So just to finish up my part, the NCCR is really about building international and multidisciplinary approach to this idea of technology in architecture and construction. We have a mandate to have direct technology transfer to colleagues in industry. So, of course, being a Swiss national institution, we're very focused on supporting our colleagues in Switzerland, but we also deal extensively with international groups. We validate our research under real-world conditions because we understand that this is the only way that we can convince our colleagues in industry that our technologies are ready for prime time. We have an education and training program because we also understand that industry is very concerned when adopting new technologies, that there's also a steady supply of people who are ready to use those new technologies. And we have a very strong international and cross-institutional outreach program. So just the last couple of days, I was at the Design Modeling Symposium in Versailles. Today I'm here. In a couple of weeks, we're in Boston. A couple of weeks after that, I'm in Australia. So we're really reaching out to people to make them aware that these technologies are here now, that they're coming into industry, and we're very excited to engage with people to bring that into the forefold. So that closes my part of it. I would now like to hand over to Hannes, who will present to you some of the more interesting work that's going on, and we'll take questions together at the end. Thank you.
Yeah, very warm welcome also from my side. And I will detail and give you more insights into the research that is partly a part of the NCCR, but is done at our chair for architecture and digital fabrication, run by Fabio Gramazio and Matthias Kohler and myself, Gramazio Kohler Research. So when we started in 2005, the digital was mainly understood as the virtual in architecture. So the question, of course, is then, when you are in a Swiss building culture celebrated for its architecture, such as the thermal bath by Peter Zumthor, also think of Herzog and de Meuron, Miley Peter, other practices. How do you materialize the virtual? How do you turn the digital data into a physical phenomenon? So our ambition wasn't so much to use the digital as a way to generate more virtual forms, but to investigate how information drives the material world. So we coined this digital materiality. So what you see here is one of our first projects from 2006 with our first robot, a KUKA robot on a linear axis. And what does this robot do? It basically rotates each individual brick in a unique angle. So imagine if you did that on site, the laborer had to measure each individual piece, had to look at the plan, check against the plan, and place each individual piece. So it's not economically viable, but for the robot, it's actually a perfectly simple task because he's fed with a set of data in regard to location and rotation, and it simply places the bricks piece by piece. So this is the start. And from the beginning, for us, it was important to embed our research within the Swiss building environment. So here, a very early project from 2006, where we contributed these wall panels to a winery designed by Beard and de Platzes architects in Christine. So that was the start. And now a big leap forward to our largest project to date, the sequential roof, which basically covers the top level of our institute that Russell has already shown. So the Institute for Technology in Architecture. So what you see here is basically a timber construction, a timber frame beam construction. It covers 2,300 square meters with these subtly undulating curves and forms. But imagine if you have 50,000 individual timber slats cut at a bespoke angle. Imagine what that means for the construction site. This is an example for a golf club by Shigeru Ban, together with Pluma Lehmann, who did the engineering and the fabrication. You end up with a gigantic puzzle. And if you have 50,000 pieces, it cannot be managed anymore. You can tag every single piece, you can have very skilled laborers, but it will be very, very difficult and costly to assemble this. So for us, the challenge was to develop an integrated process that really works from the design, from the computational design, all the way to the fabrication, taking into account that it's robotically executed. Yeah. Yeah. Seems to. It's a video that should start. Ah, here we are. So sometimes it's the simple technology that lets us down. So let's focus again on the more complicated technology. So what we did is to develop an integrated process where the portal robot that the company Erne, a specialist in timber construction, bought, And this portal robot lays out these bespoke cut pieces. You can also already see the kind of the form of the timber frame beam, and step by step, like a 3D printer, it places the pieces. It also nails them together in an integrated process, so it's an integrated tool. You can also change its tools, so with a circular saw, so that you cut the end pieces. And so you nail these pieces together, which means you basically change the complexity of 50,000 pieces to 168 pieces, 168 beams, that you then can fit out with the sprinkler system and all the services you need and you are required by the building norms. And then you basically bring them on site and you locate them in a conventional manner. So here you see the fit out with the sprinkler system. The construction is actually, the building system is actually a very simple, straightforward system. So from a structural engineering perspective, the roof isn't the most advanced roof, but the intelligence is really in the robotic process, in the integration of the process from the design all the way to the construction site, where then these beams arrived last summer in 2016 and completed our institute building. So the key to the project is really what you see here. And what you see here, you actually don't see, because it's just a representation of data. So we never created a plan that we handed over to the company. This is purely for representational purpose. So what you see here is one joint with the nailing pattern that holds together the slats. We had 1 million nails that needed to be positioned according to the Swiss norms, so to take on all the stresses. So what we did is we wrote an algorithm that randomly placed the first nail and then calculated the position of all other nails, because in this very situation, we don't want to hit the nail on its head or on the head of the other nail, right? So this is the challenge, which then results in this image or representation of the node. So when you think about these robotic facilities, it's not just about the hardware, but it's also the software through which the intelligence is introduced to the project and to the design. So to move one project on, I want to present you Mesh Mold. Mesh Mold is one part of the DFAB house that Russel has already presented. And it's this S-shaped wall that then holds the smart slab, a concrete slab, and 2 stories of timber. It's a project about concrete construction. And as you know, when you have very elegant shapes, like for the Rolex Learning Center, and you want to do these elegant shapes in concrete, you end up with a not so elegant construction. You end up with a lot of effort that goes into the formwork. And of course, that basically means you build the house twice. A timber one, and then a concrete one, and then you get rid of the first one. So that means, again, you have a lot of labor-intensive process. For the Rolex Learning Center, the formwork was still assembled by hand, even though it was driven by digital data. And of course, you have an unsustainable process generating a lot of waste. So we wanted to change that and look ahead and develop a more sustainable approach. And what we said is, well, you have the rebars inside the concrete. And we want to use these rebars, dissolve these rebars into a mesh, And the mesh can then withstand the pressure of the viscous concrete. So we did a proof of concept study, as you call it, a few years ago at our lab in Singapore. Here you see this thermoplastic mesh, where we then poured the concrete, compacted it, and it showed us that this mesh, this very, say, thin mesh made out of thermoplastic extruded by a robotic end effector, could withstand the pressure and the load of the concrete. So for us, that was a start into a long research project that would then become part of the NCCR. That way allowed us to collaborate with the Agile and Dexterous Robotic System Lab, which then again allowed us to develop this end effector for the robot, where we're now able to cut, bend, and weld 6mm reinforcement bars. So here we see the process. You've already seen the in situ fabricator, our mobile robot in Russel's presentation. So here you see the machine in action, how it vertically, step by step, welds this mesh. So it's like 5 to 6 centimeter long pieces that are cut and then spot welded together. Now, this is in a lab. It's an environment that is fairly controlled and safe and stable for a robot. So this is the, say, the easy part of it. But then we packed it up, the whole system, the robot, the controller, the end effector, put it into a container and moved on site, where we executed then the computationally designed wall. So again, it's this S-shaped wall, and here you see how the mesh was generated in order to take on the specific load cases with these subtle undulations that locally respond to stress. And so we went on site with our robot that has a visioning system to locate itself, so it knows where it is. It has cameras that check and control what it does. Takes in all the data we send to the robot, and here you see the end effector in action, how it spot welds these small pieces, cuts them, and assembles the wall. It's a nice wall that unfortunately will be buried. So then, once it has been completed, but now in October we're going to fill it conventionally, and then finish it, and then it will be a nice exposed concrete wall. Again, it might look very sophisticated, but it's really the start. We're now at a level where we are very much in control of the process, but again, if you think of moving it on site, building large constructions like the Rolex Center, there's still a long way ahead of us. But of course, we can say, well, is it still the right time? Is it still the future to focus on concrete, for example? Don't we have to think radically different and explore systems that are even more radical or unconventional and really challenge our beliefs and our paradigms? So in a way, we always move between avant-garde and culture. So avant-garde being few, being ahead, and culture meaning transporting, mediating these ideas to the wider community, to the industry and the culture. So JAMmed is a project that basically holds together loose gravel by laying string, robotically laying string. So it really informs loose material. And basically it works like a multitude of belts that hold together that loose gravel that wants to kind of move. And in that way you can stabilize the system under a loading condition, where then the small gravel interlocks, so it forms stable structures. So amazingly, we can put 10 tons, 17 tons, we put it on the load testing device, on a 40 centimeter in diameter column, just made from loose material, gravel and string, the string that you can buy in a Swiss post office or in a French supermarket. You just buy the string and you use normal gravel to build these structures. So the first time we exhibited this was 2015 at the Chicago Architecture Biennial, where we used Misapur foam glass gravel, which is lightweight because we couldn't put that much load on the floor. But the amazing thing is that you can build stable structures with that system. But once you're tired of it, or once the exhibition has finished, you simply wind it and you end up with a heap of gravel and string. So in a way you could say it's really a kind of architectural or structural perpetuum mobile, where you constantly rebuild the structure. And of course, from an architectural perspective, loose material has always resulted in a heap. And now, through the placement of string, we're able to inform the loose material in such a way that we can turn it into architecture. So we've continued this research and we are now working with real gravel, and we are actually working without a mold. So it's a moldless system that is solely based on the pattern, on the way we lay the string. Now if you think this is crazy, it might get even crazier. So a classic in our field of digital fabrication in architecture is the limitation of the workspace. So you have a machine, for example a 3D printer or a robot on a linear axis, and it has a certain work range in which it can act, which means you have to build parts and assemble these parts. Now the question was then, how can we exceed that workspace? How could we go beyond that workspace, not using a conventional portal system, which we have also installed in the robotic fabrication lab? So what we thought, what could work is, if I cannot reach, I can throw. But of course, this is a kind of tricky task, and when you think of the history of throwing and the science of ballistics, then shooting has always resulted in destruction. For thousands of years, it was turned against architecture and wasn't working in favor of architecture. So we, in a way, civilized, disarmed the process, and with the help of sensors and feedback, got on top of the problem of ballistics. So basically we have a small robot, we shoot, we control whether this is right to what we calculated, we improve the calculation and the shooting apparatus, and we shoot again. So what we did is, at an art institution in the east of Switzerland, we extruded many clay projectiles, clay guns, and we used them to shoot them to build walls. So when you look carefully, you see how these buckets of clay land and form rather slender walls in the axis of the shooting. So here they come. And while it might look very playful, it also emphasizes the importance of feedback systems, of reading what you've built and feeding that into the loop, so to learn basically. And this is also a big topic in our field, the whole area of sensing and machine learning. Now this is the machine, very simple, a small UR robot with a pneumatic pan. Here goes the clay, and then you shoot according to your computational model, day and night, and you end up with these structures that in a way show that very archaic material, natural, sustainable material can be combined with high technology. So it's a different understanding of smart materials, it's smart processes, it's our intelligence that goes into these processes and hopefully create a better and more sustainable future in construction. Thank you very much.
Thank you very much for this amazing presentation. A lot of information, a lot of projects, very exciting. So, do you have questions in the audience?
Yes, hello, thank you for that. I just have one sort of technical question. When your string structure, it looks like the string is being glued, or is it just cast around? Because if you could sort of explain, because I saw an image with the line going around.
No, there's no glue, no mortar, no binder involved whatsoever. So it's really just the gravel, and it's the string. And when we moved it from the load testing device and we basically layer by layer excavated to investigate what's in there, we realized that the string is actually cut in many short pieces. So eventually under pressure when it compacts, it's really the rock that interlocks, and the string in a way has an only intermediary function of holding the gravel together while building it up. But we have no formwork, and we only have string and gravel. As surreal as it might appear, but really that's just it.
The science behind it is all about slump angle, right? Different materials have different slump angles, and if you change the granularity of the gravel, it will have a different slump angle because of the way that it sets on itself. Now, what we're doing is we're adding very micro amounts of tensile members to retain the gravel in a particular pattern, such that the slump angle then is dependent upon where the string is, as opposed to where the rock is. So it's still completely under gravitational loading. We just change the slump angle by adding small amounts of tension in very precise places. Once the gravel is loaded, once you put a weight of the gravel, the string has no bearing whatsoever. And you can even, under loading, you can go in and just flick your finger on the string and you realize that there's no tensile force there because all of the force is being transmitted through the jammed matrix of gravel.
Just out of curiosity, is there a story behind how you came up with this string? Because I'm sure there is.
It's a very established field of research. So jammed structures. There is an academic community that investigates these. There's also the groups we worked with of Falk Whittel and Hans Hermann, who investigate the behavior of granular material. They, for example, research the behavior of dunes. And we, in a way, collaborated and found an expression and, in a way, changed scale. So we often do that. We basically scan for exciting ideas within the within the sciences. Of which we are part of, and of course we are part of ETH, so we are very much at the center of a research, we are a research center, And so we tap into these ideas, collaborate, and ask how can it turn into building systems that have value for architecture and construction.
I mean, I would also like to point out, I mean, maybe when you look at this project from a structural engineering point of view, a lot of what we do in construction is we identify where we need to place mass. So, for example, if you look at these structures, maybe they remind you of kind of the placing of mass in trussel bridges from the railway systems. But we are also constantly looking at ways of developing new recyclable, sustainable construction systems. So I would propose to you, for example, one of the applications that this might be very useful for is in the reinforcing of very, very thin formwork. So if you want to cast a very precise concrete wall, typically you take a big, thick plate of structural steel and you cast against that because the structural steel can resist all of the forces against it. But then you have this plate of structural steel which is cut to a very particular size, and it's basically a piece of waste afterwards. You throw it in the recycler, you melt it down, you invest huge amounts of energy in making it, and then you invest huge amounts of energy in recycling it. What if you took an incredibly thin veneer, but you placed that veneer against a 100% recyclable string and gravel block of mass and then poured your concrete against that? You could still have a very, very precise, very pure concrete wall according to architectural specifications, but then you could pull the string away and take all of the mass away and you'd have just the garbage of that veneer. And so it's really, for us, it's about coming up with crazy ideas and then also figuring out what they might be useful for thereafterwards. And so when we present these crazy ideas, when we present the ballistics construction methods to you guys, I hope you will also think of, you know, new ways that you could accomplish tasks which normally would be energy or material or labor intensive, and think, oh, you know, if we just take, for example, time as a factor away. You know, it takes 3 days to build up those relatively simple ballistic walls. But if we take time away and we realize that we're not paying for labor, so time as a cost equation has a much lower value. If we do things like that, are there different ways that we could conceive of the problems that we face every day in construction and architecture?
I have a comment for you, Russell. So, and it's a kind comment, so please don't take it personally. But you said that engineers were objective and architects were subjective. And although I totally agree with you, I must say that you're totally prejudiced.
Well, I'm both, right? So right, I get to be prejudiced.
Excellent. In the beginning, you mentioned that, and besides, you succeeded in putting together architects and engineers in the same room. And you've done that by putting contractors outside of the business, right?
I wouldn't
with
say
the robots.
That. We actually have quite a few industry collaborations. And again, what I also said very clearly is that one of the biggest challenges that we faced in getting this thing set up was getting all of the different disciplines to talk to each other, but to find a common language where they understood what was important to the other discipline. Not just stating what was important to the project, but when you're talking about a research field, a lot of these guys are PhDs or postdocs who want to write papers and so on, and they have certain findings that will place them within their own discipline. So that's kind of a personal priority, and then there are project priorities. And so also with regards to our exchanges with contractors and with people from industry, not just in the construction sector, but also in robotics or in control systems or other sectors, we have to figure out what is actually important to them, such as they're able to make an investment into the project, which is important to us.
Thank you. And you mentioned in the beginning that robots have a drawback, is that they respond to orders, but they're very little adaptive on site, right? And what is good, I mean, what is what we ask from construction companies and workers on site is to be adaptive and correct things as they see and adapt to their environment. And Hannes, you mentioned that in the end, that your recent research would be on adaptive robots, or you talked about machine learning. Could you comment on that and build up and say if your vision in the end is that the robots will definitely take the place of workers on site?
It's for us, it's a man-machine collaboration, and because the robot doesn't do anything on its own, right? So all the intelligence that makes the robot successful is our human intelligence. So the robot in itself, I think, doesn't take jobs. It changes the jobs, and it changes the way we work on site. So now in regard to the sensing, that is, for example, also a way that if you look at Japan, but also if you look at robotics, that man-machine collaboration is really an important issue. So how do you make these processes safe? Because we're working within a research environment and we're working in manual mode, so you're not going in automatic mode like you do in the automotive industry, for example, or in manufacturing. But in order to collaborate, you also need to develop the sensing and the control which actually allows that collaboration. Also, if you want to work with several robots, they don't know of each other. You need to tell them how they interact and how they behave.
They can learn.
They can improve their behavior. But again, you need to tell them, right? So also machine learning doesn't exclude the human intelligence. That's say all the science and the knowledge that goes into it.
I would say something kind of bold here. First of all, Star Trek and Star Wars, they're not real. There's a huge perception that robotics is far more advanced than it actually is at the moment. So one of the major challenges that we face is really in this area of getting robots to understand contextual awareness. And contextual awareness is everything from knowing what is happening in their immediate surroundings, but also being able to contextualize, being able to understand what is happening in their surroundings. Perfect example is, say, our tracked robot is driving down a road on its way to the construction site, and somebody drops a shovel in the middle of the road. The robot needs to understand whether that's a shovel or whether that's a construction worker who's lying down and fixing, I don't know, a piece of conduit, and whether it can drive over that thing or not. Now, the sensors that we have right now, most of them are either optical or geometrical sensors. They're not measuring the softness of tissue or whether the thing on the ground is giving off heat or whatnot. So if you talk about machine learning, we're not where you're talking about it at the moment. The research is definitely headed in this direction. And in the last, I mean, you saw the 2 covers of The Economist magazine. In the last decade, I would say, the cost of computation has gone down to almost nothing. Computation is the key to driving all of these sensors. These sensors are now, their costs are going further and further and further down, and we now have the ability to compute what it is that the sensors are giving, the feedback, the data that they're giving us back. We can now find a contextual reasoning and an understanding of what those sensors are giving us back. But we're right at that point where we're now starting to be able to put multiple different types of sensors, whether it's infrared, whether it's spatial, whether it's softness, whether it's linear, whatnot. We're able to put all of those different types of information together to understand the context. We, as humans, do that in a heartbeat. We know that this is hard and that this is soft. We know just because we have so much experience. We've built up a lifetime of programming, and we also learn from the lifetimes of other people who have given us all that data. We're not at the point yet where machines have that ability to absorb information, contextualize it, place it within the realm of their sensors, and be able to compute an answer in a heartbeat. So this is the crux of a lot of the research that we're doing. And this is also why when we say, kind of in my career, I don't expect robots to be on site doing a complete building. I always expect robots to be working with other people who will be able to problem solve the situations and for them to be adaptable.
But what you realize and what we realize is it's ultimately a question about skilling. Right? It's skilling the workforce, it's skilling the engineers, it's skilling our future generations to understand these processes. So this is really key. right? We need to make architects understand the digital. We need to make the politicians, the construction industry, the wider society understand these processes. So the construction sector and architecture can be transformed and adapt. And this is really also the challenge for bigger companies and enterprises, to make people understand these challenges, but also embrace these challenges in a positive way. And I think then you can move ahead.
There's one other thing that I'd say on the topic, and because Hannes mentioned the car industry. So robots have been in the car industry since the 1970s. The reason that robots work very well in the car industry is because they do serial production. They do the same thing again and again and again, and you can spend 2 or 3 days programming one robot, 2 or 3 days of time programming one robot, but then you let that robot run for months just cranking out exactly the same thing over and over and over again. The area of research that we typically work in is architecture. And architecture, if you crank the same thing out over and over and over again, you have a problem. But there are other areas in the construction industry where this is not the case. And you guys, your société is very involved in some of them. So things like bridge design, things like tunnel design, where you have long linear structures where you need the same element again and again and again. If you start to look at prefabrication, or if you start to look even at on-site robotics, where they can take advantage of repetitive construction, that's where things start to make sense. That's where things start to have value of feedback.
So you're pushing robots to be from objective to subjective, is that right?
Well, not the robots themselves, the handlers, clearly. I mean, we want you guys to stop doing the mundane, dumb tasks that you have to do again and again and again for a project, and we want you to think of the creative way that you can solve the project as a whole, such that again, if you change the position of one nail in the roof, the entire roof recalculates and you still have a viable structure. This is what we think of is the future of architecture.
Going back to the beginning of your presentation, there was a slide showing the productivity increasing drastically over the last 20 years in manufacturing and then pretty much stagnant in construction. Mm-hmm. So both your particular project, a 12-year project, and in general, your colleagues and everybody working on robotics, what kind of inflection do you expect on the construction curve thanks to your work? What is your ambition?
A very shallow one. No, we're fundamentally aware that the construction sector is a notoriously late adopter of technology, and that it is incredibly risk adverse for very obvious reasons. And that for the construction sector, explicitly the architecture sector, but in general the construction sector, for them to adopt technologies, they need a helping hand to show that the technologies are ready. But we also know that it's not only showing that the technologies are ready, but it's that there's a steady supply of labor who knows how to engage with these technologies, that there's a steady supply of architects and designers and so on who design to be able to kind of use these technologies in a more adaptive, economic, optimized way. We know that there are a great number of links in this chain, and personally, this is, I believe that this is part of the reason why the Swiss National Science Foundation has funded us, is to be able to prove these things again and again to people in industry, such that they're able to take small steps, but that small steps should build a momentum over time. And the 12-year time period that we have for us is really a start. I personally believe that this area of expertise is actually going to become a discipline unto itself over those 12 years. That, you know, kind of we're at the 4-year point now. In about 10 years from now, I believe that you will have jobs such as robot wrangler on the construction site. You know, the guys who are responsible for making sure the robots know what their task is that day and making sure that they have the materials or the information or the data or the power supply or whatever. And that will be a vastly different job than a construction laborer. Likewise, there will be architects who know how to program CNC code directly for the types of robots that will be on site. You'll bypass a whole bunch of steps of shop drawings and so on, and you'll be able to take data from design and put it directly to the production on the construction site. And there will be maybe specialists either in the engineering office or in the architecture office who will be able to do that. So the jobs will evolve and they will modify. And we are a catalyst for this to happen, but I'm sure that it's at the end of our 12-year mandate, it's not going to be in place.
Yes, thank you for your teasing presentation for what might be the future of our profession. But do you have other real-world examples that we can examine and just see how it will be turned into rules, well, calculation rules and regulation way of construction, and how our robots will evaluate their work? And the question behind is the responsibility of robotics into construction world.
This is an extremely important topic. The question of responsibility, the question of insurance, the question of the long-term durability of these constructions. There's over a decade now of kind of digital architecture that has been built using these techniques, as well as things like prefabrication using CNC and so on. I mean, everything from Frank Gehry from 15 years ago through to today, we've seen the technologies evolve. And the technologies have often evolved based exactly on this, as to how you can guarantee the quality of the output such that the engineers or the architects or whomever in the end is fundamentally responsible for a piece of kind of urban infrastructure or urban fabric, they can guarantee that to the level of building code. So wide range of projects. A number of the projects are here in Paris. There are a wide range of projects from around the world. With respect to robotics themselves, we're at the very beginning of that. I think Hannes showed a couple of projects now really out in the real world. We're seeing more and more of them happening. What we see in other places in the world, to be kind, is where robots are one-to-one replacing workers, where they're doing exactly the same construction, but they're doing it using technology. So whether it's the placement of bricks or whether it's 3D printing of concrete houses in China or whatnot, where the architecture itself is not being changed, but the process on how they achieve it is being changed. And this is kind of a safety step, because if you're still outputting the same thing, then it's still tested in the same way, it's still guaranteed in the same way. What we're very interested in is not putting out the same thing, in figuring out what you can do differently because of these technologies. And so this is why we're kind of also step by step, slowly and surely coming into the marketplace. But we're still definitely in our infancy.
But also, for example, the company that bought the portal robot and built the timber roof, the sequential roof, the robot is in constant use, but of course, as Russell said, the reality is 80% maybe of the time it runs standard tasks. But it's also the potential of the robot that it doesn't differentiate between standard and non-standard. So of course, from a point of investment, there needs to be a return. And that return is safeguarded by being able to run standard tasks, do standard elements that just run basically as a background process. But then also having the opportunity to offer solutions for the rising complexity and also scale that we are facing in construction and in architecture.
I mean, a very good story about this company is that when they first won the tender to build this roof, they were asked, how are you going to build it? And they said, we're going to hire 50 carpenters and print off very big plans and kind of lay wood down according to the plans. But then they did a cost analysis, and it actually cost them the same to buy the portal robot, install all of the functionality, and hire the group that would actually program the geometry into it. And by hiring the group that would program the geometry, they also trained their own people. So by running this project, they effectively came down to a net zero capital investment because the project paid for the piece of infrastructure. Now they have the piece of infrastructure, and as Hannes said, basically what they have is a new business outputting prefabricated, square-framed timber panel walls. And they just, every time the machine is not being used for something, they just print off a whole pile of square, prefabricated interior partition walls and sell them off at a quite good rate for the buildings of high-rise buildings, residential buildings, and so on. When an architect comes to them, though, and says, I have this idea for an incredibly complex structure, they can then turn around and say, okay, these are the conditions of the machine. This is what we're able to build. And the architect can then adapt their planning, adapt their geometry to what is possible for that machine to build. And at the same time, the company then gets a lock already on that project because they have the machine that can build the geometry the way the architect has designed the geometry. And even if they put it out to bid for a wide number of other companies, then those other companies are already at a tacit disadvantage because they don't necessarily have exactly that machine. So it's also looking at it from a business point of view as to what you can accomplish by making very straightforward investments and knowing in the end that you're going to be able to take a step forward and secure your market.
Question? If you want to push the outside of the envelope and say how much you can do with this robotics, you said that you can improve the process of construction. You can do it cheaper, faster. So maybe not yet, but in the end.
I never said faster.
In the end. All right. And the other way is to do things that you cannot do at the moment, like complex structures. Are there any further developments that you envisage beyond complex structures, complex forms, or efficiency in the construction process?
I mean, in a way, we're actually not so much interested in automation, because as Russell has already said, there are always like two options. You can use new technologies to make existing things easier and more efficient. Fair enough, perfectly viable. Or you can use new technology to explore new realms. Now, as a research institution, we focus on the latter. So what interests us at the moment, I think what Russell said in regard to context. So in a way, in architecture, there was an understanding of contextualism, which was you read the neighborhood, you understand the site, you understand what is going on around the place where you build something. I think that will be the area of digitalization in the years ahead, that we develop a form of computational contextualism where we can feed all this data we know, and which is not just, say, rational geometric data, but also qualitative data, airflow, the quality of air in general, all kind of aspects that we might not yet know, and feed this data into the design process and somehow capsule it in the design and fabrication process. So because when we look back, what the robot did is basically it created for us, or our invention was in a way to use it as an outlet for data to be turned into physical material, into built form. So now with all the development of data collection and massive data and all the words, you know, we can basically feed that data again into the process. And of course, what has happened, and which is also very important in terms of a change of the culture, is that the data will be out there. So the research we do as a public institution will be publicly available. So also the SNSF, the Swiss National Science Foundation, pushes towards open data. So you don't just write a paper, you also publish the data, you publish the code. And that means basically all this chunks of knowledge, these rules and commands and that drive robots, that guide us on site, they're publicly available, and you can use them to basically adapt them to your individual case. And I think that will maybe have an impact like the internet, where you Google and Wikipedia answers your question, or a database answers your question, and you can readily access very specific information. So I think there is a lot, or there will a lot happen in the future.
I think also, to give a much more pragmatic answer to your question, is, for example, the integration of services within building components. If we take a page from our colleagues in auto racing, for example, they're now 3D printing engine components. They're 3D printing kind of big chunks of metal that are intricately designed, that can only be made by 3D printing. They can't be milled, they can't be machined, but they integrate, for example, all the cooling and all of the mechanical systems already within the component itself. So one of our projects, the Smart Slab, which actually sits on top of the mesh mold wall, is the idea of 3D printing concrete components. So in this case, it's a very thin shell, but it also has printed into it the conduit chases, the air chases, and the hydronics chases for the heating, already printed into the components, such that you take a component, you assemble them on site, you fill the pan with concrete, and then you already have your pre-plumbed building components, and you don't have to then waste additional space in a drop ceiling or additional space in a false floor for all of these components. They're already integrated into that space. This relates to a project by Philippe Bloch, one of the professors, which is called 3 for 2. And this is the idea that if you can reduce the size of your floor slab, still maintaining the structure and embedding all of the services within the floor slab, you can actually get 3 floors in the space of 2 floors and still have the same floor to ceiling height. So in terms of real estate, you're still building the same thing, but you're getting an extra floor for every 2 you build. All of a sudden, you get 1/3 extra saleable space in your high-rise buildings. All of a sudden, projects that couldn't be financed or couldn't be financed in a particular way, they become realizable. And this is really where these technologies can bring intelligence back to architecture and make things possible that weren't possible before. Not just from the material, not just from the technology point of view, but also from the financial, economic, labor, construction point of view.
Okay. Other questions? No? I had just one additional question. So you said that, I mean, your research was oriented towards doing new things, but still you offer, a limited number of new tools. So how do architects react? I mean, because is it not this a way to standardize the way they think architecture? They are limited by the tools you're offering, or do they think it's a great opportunity for them to do new things? And
I think it's certainly an opportunity. But of course, if you say, for example, you've got the process for building the roof in place, now we could build an endless amount of similar roofs. Mm-hmm. The architect might not buy into it if he cannot claim authorship, right? So this is maybe also how the role of the architect changes. So we understand the architect as the sole author, like say an artist, right? Mm-hmm. And the artist draws a sketch and hands the sketch over, and then it's turned into a design, right? So I think new generations will be much more aware of the digital process. And I mean, we are working towards a fabrication-aware design process. And as you say, it's a tool. So the fantastic thing about, for example, a robot is that it's basically just an industrial arm. It's not even the hand, right? That's just a gripper. But we can design that tool. It can be an extruder, it can be a nail gun, It can be anything. This is why a 3D printer can suddenly turn into a robotic setup and be scaled up. Or we can use it to robotically fabricate slip cast processes that we also research and do. So I think it offers a wide variety, and at least recently we've been approached by many architects, and we are architects ourselves. So of course we are eager to explore what can be done, offer new tools, develop new processes, but as I also said, in a way create awareness amongst architects how these processes can be used and integrated, and hopefully also by doing that, working on the interface between architect and construction industry, right? Again, what Russell said, bringing people together, making them understand each other. And I think the digital, what is so amazing about the digital world is that a physicist or a material scientist, he works in the digital realm. We as architects work in the digital realm. And we might both code in Python as a language. So then the two worlds can be combined because we speak the same digital language. And this is the amazing thing about the digital world, that you can fuse the knowledge and develop these integrated processes, say software frameworks that really capsule all the intelligence like in a brain, right? And that brain then runs in a way the construction process. You could also say it's an ambition to bring the risk up front, so to not have the risk on site where it's happening live, but to actually have the risk in the beginning, and then simulate and calculate, have like in building information modeling, right, to have a full picture of what will happen, and then basically you run it.
I mean, your comment about tools makes me think of Maslow's hammer, right? Maslow's hammer, where if the tool that you have is a hammer, everything becomes a nail. So what if you as an architect have standing behind you a mechatronics engineer, a roboticist, a control systems engineer? What if you're a team rather than an individual, and you can make whatever tool you need? Whatever tool you need. And if you need a bigger robot, then you source a bigger robot. If you need to lift 1 ton, then you source a bigger robot. If you need to lift only 10 kilograms, then you source a smaller robot. If you have the tool and the ability to position that tool accurately within sub-millimeter tolerance anywhere in 3-dimensional space, all of a sudden you have an amazing creative potential for whatever it is that you want to make.
Okay. Last question, maybe? Julien?
I would dare saying that Swiss architecture is mainly boxy architecture. So you were mentioning Herzog and de Meuron, Peter Zumthor. Have you submitted them your research and already seen some interest?
If you look up any of my academic papers online, you'll see that I wrote a lot of them with a gentleman named Dr. Kai Starelke. He was the head of innovation at Herzog and de Meuron for a decade. So yes, we are very aware of the boxy reputation of Swiss architecture, but I would point out that the Beijing Stadium is not boxy. I would point out that there are quite a number of very elegant structures by, for example, Calatrava, who trained at the ETH. So although we may have a reputation for square and simple, that square and simple actually comes from the very strong tradition of engineering within Switzerland. And the box, the square and simple, comes back to the appreciation for very, very high quality. So Swiss architecture is also known for being very solid, being very, very well built, and also incredibly expensive, I might point out. But when we talk about the capabilities of robotics and we talk about the capabilities of the digital and the precision that is embedded in that design data, then there is a correlation. And what we're saying is that we would like to be able to build expressive forms with the same degree of quality, with the same degree of precision, with the same degree of solidity at roughly the same cost, but these technologies will allow us to do it in this kind of expressive and free-form way.
I mean, what is actually great about the box, it's a very precise and recognizable shape, right? This is why everyone knows the Swiss box. But for our processes that tend to be maybe what you could call chaotic when you think of jammed, is basically that it tells us how precise we are. If we can build a perfect square, a perfect Swiss box using that technique, it basically means we have full control over it. We're not gonna say, the heap is an architecture. No, we turn the heap into a box and then we say, okay, now we have architecture, right? So in a way, that way we benefit from that culture that is about precision, it's about control, it's about understanding the process, being very thorough in doing it. And the basic shapes help us to do that. If you have a crazy process and a crazy shape, you might not understand what it is about. If you have a crazy process, but a very recognizable, archaic shape, you know there's something different, right? So this is how it helps us, and how Switzerland as a place for us helps us to drive our research.
One last word on the brick, because we're known for placing bricks, right? All of these walls that were done at the very beginning where the bricks are rotated and so on. Please understand that we don't love bricks, right? Bricks are the perfect construction proof of concept. If you can show that you can pick up a brick and place it exactly in a position in three-dimensional space, then you can also pick up any other tool, any other extruder, sprayer, glue gun, whatever, and also position it exactly in three-dimensional space. Now for us, the value of the brick is that when we invite industry to come and see what we're doing, they understand that the brick is a construction material. They understand it immediately as being architectural construction. And so we use the brick as a way to prove that we have control over the technology, while at the same time showing the construction industry that we can build in real-world materials at real-world scale in real-world ways that will hold up to the codes and so on. You'll notice that the brick walls that we did were flat and they were square. They're patterned, they have all kinds of intricacy of information embedded in those walls, but they still fit into the conforms of the Swiss box, as Hannes demonstrated in the winery project. So for us, it's about being able to control the information, it's about being able to control the process, it's about being able to control the materiality that results in, but at the same time, still achieve the highest level of quality that befits our industry where we come from.
Okay. Hannes, Russel, thank you very much. It was a really exciting conference with a lot of food for thought. And for sure, in SETEC, we will continue to follow up closely what you're doing and try to be part of one of these exciting projects. Thank you very much.
Yes, let's...